Okay, so it's my great pleasure to introduce Yanli Song from Washington University in St. Louis. He will talk about case series of the reduced system algebra of a real reductive legal. Okay, Yanli, please.
Okay, thank you. Thanks for give this opportunity for me to present my work. This is a joint work with Pierre Claire, Nigel Hickson, and Sean Tang. So this project, actually, we have been working on this project for several years, but it takes us a long time to finish this project. But I think now it's ready, and I think this our preprint will be available next week or maybe in 2 weeks. Okay, so I think it's good time to tell you what we have done. So our motivation is to understand this Kasparov theorem. Of course, this is it originates a conjecture, but it has been proved by different people like Lafolk, Wasserman, and Shepard, Nestor Hoff, and Richard Nest. And here we are just following the original outline given by Wasserman, and trying. What we did here is to using the representation theory and complete some missing part in Wasserman's the plan, the outline to prove this Kasparov theorem. Okay, so in my talk, this G is a connected linear real reductive Lie group, and the reductive, in fact, the reductive here really means is that you can take G to be a connected subgroup of GLNR, and reductive here means that it is closed under taking transpose. And the K is the maximal compact subgroup of G, and because it's linear, you can just take K to be the intersection of G and ON. So the examples you should keep in mind are just GLNR. These are matrix n by n matrix in R such that its determinant is non-zero, or SLNR, which are the matrix whose determinant equal to 1, and also GLNC, SLNC. Other classical examples are SOPQ, SP2NR, something like this. Just a classical linear reductive Lie group. Okay, so that to state this Kasparov, one thing we should consider is Dirac operators on symmetric space. Suppose we have E. E is any irreducible. Does not have to be irreducible. It's just any unitary representation of the maximal compact subgroup of K. And we can define a vector bundle. So it's just G times E over K. So this is a vector bundle on the symmetric space Gma K. So that here I abuse my notation. I will just use this E to denote both the K representation and the vector bundle on the symmetric space. So we can form a L2 space, L2 of Gma K, traced by this vector bundle determined by E. And this L2 space can be identified as this one. Just here we use the right K action on G. So these two spaces are the same. Okay. And this is the helper space on which the operator acts on. And we will have the Gaudian decomposition. So G is the Lie algebra, real Lie algebra for the group G. And the K, little k, is the Lie algebra for the maximal compact subgroup K. And S, little s, is the complement of little k in G. Okay, so this is known as Gaudian decomposition. And a spin module is a finite dimensional Z2 graded Hermitian space equipped with the action of the Clifford algebra, and also this action of the maximal compact group K. They should act on this space in a compatible way. Okay, so this is what do I mean by spin module. So this spin module in general we will denote by S. So S has action of Clifford, little s acts on here, and K acts on here in a compatible way. Okay. And if S is a spin module, it is also a K representation. So we can form a operator. Oh, so we can form a vector bundle. So we have this space, and because it has the action of the Clifford algebra, we can define the Dirac operator associated on this. So this Dirac operator will map to this space to this space. So this is the Dirac operator acts on the symmetric space. Okay, so this Dirac operator is essentially self-adjoint. It's actually here, this S has a Z2 grading, S plus minus, it mapped its odd operator, it mapped the plus part to the minus part, mapped to the minus part to the plus part. And this its kernel will be a closed subspace, and it's always the case. The kernel will be, it may not have kernel, but if it has a kernel, then its kernel carries, it is a unitary representation of G. Okay, so this is the Dirac operator on the symmetric space. Because we write it in this way, and oh, one more thing I should say about the spin module. So if S is even dimensional, then if it is an even dimensional real space, then there always exists unique, there's only one Z2 graded representation, irreducible representation for the Clifford algebra. And but if G mod K is a spin, it's equivalent to say this spin representation is also a representation of K. And in this case, spin module is always in the form of the tensor. So this fancy S carries representation, carries the action of the Clifford algebra, and K acts on diagonally on this space. So in this case, if it is a spin, but in general, if G mod K is not a spin, this one fancy this may not be a representation of K. So to deal with non-spin case, what you need to do is to, because K acts there on the, so this S is the Gaussian decomposition. G is the K, that some with S. So if it is not spin, you can always, this spin S is always a twofold cover of the SOS, and you can, in this way, this map acts on the this, so the K has there's a map from K to the SOS, and you can get a pullback. So this is a twofold cover. This K tilde is a twofold cover of the compact group K. So that in this case, you should still form something like fancy S tensor with E, but in this case, E should be a representation. In this case, E should be a representation of K tilde, which is not a representation of K. So that so this their tensor product will be an action of K. So this is how we handle the non-spin case. If it is a spin, then everything is simple. If it's not spin, you should consider the twofold cover instead of the K itself. But in any case, the spin module are easy to classify because it can be classified by the weight of K. In particular, if G mod K is a spin, maybe I will mention this later on. So what I'm trying to say is that the set of the equivalence classes of spin module are easy to classify. Okay. So now actually we can understand this Dirac operators on symmetric space from the index theory viewpoint, thanks to Harshchandra's work. This is the Harshchandra's Planck-Lev formula. So this is one version of the Harshchandra Planck-Lev formula is a decomposition of the L2G. The above is a generalization of the Peter-Weil theorem for the compact Lie group. So because the Peter-Weil theorem just says that L2 of K can be decomposed into direct sum of the irreducible representation of K tensor its due. And for compact Lie group, every irreducible K representation are all finite dimensional, and its due space turns out to be discrete. But if G is non-compact, it's not so nice. First, all the representations, most of the representations are infinite dimensional, and the due space may not be discrete. It may have some continuous parameter. So this is the generalization of the Peter-Weil to non-compact space. So here, so we only consider we are not going to consider all the unitary due, but only the temporal due. Temporal due means that the support of the Planck-Law measure. Okay, so this is a work of Chandra's work. This is the decomposition of the L2G. And thanks to the Planck-Law theorem, we can have a decomposition of this space because we have this one, L2 G mod K of the spin module S. We have this is isomorphic to this. It's plus minus of K invariant part. Use the decomposition of the L2G, we can decompose this symmetric space, the Hilbert space given by the symmetric space in the following way. In the following way. So here we just use this formula to decompose it. Here the K action, we use the right K action. So that is the K action come from here. So in particular, that for any spin module, this space for any representation, its tensor with S plus minus take the K invariant part is always a finite dimensional space. So this is called a Planck-Law index formula. So that is to say that in the index, we can use the Planck-Law formula to rewrite the index. Okay, so from this viewpoint, it provides us a different viewpoint to understand the index. That is because you can view this one, as I mentioned in the last slides. This one is a finite dimensional space, and for every pi, you can associate it to a difference of two finite dimensional space. So in some sense, this one you can view this one as a sort of a vector bundle over the temporal due, because for every temporal due, you can associate with a difference of two vector space. And moreover, one can check that pi of ds it acts on this space, so it's invertible. So you have R operator acts from one space to another space, and it's invertible outside a compact subset. Here, I'm just telling you the idea. This is not very precise. So what I'm trying to say here is that the index, you can view it as a vector bundle over the temporal due. But this is not precise because the temporal due in general may not be a Hausdorff space. But in the nice case, if it is a Hausdorff space, that you can view this one as an index bundle. So it gives you a K-series element on the temporal due. So it's just one way to consider. So from this viewpoint, you can see that the G index of the Dirac operator on the symmetric space, you can view it as a K-series class in the temporal due. Here, I didn't really define regular, but if this, I will talk about the regular later on. But if it is irreducible spin module, which induce a vector bundle on the symmetric space, the support, that is to say, the support of pi of ds is concentrated in a single. The support means that the operator acts by zero. That is, the kernel will be concentrated in a single discrete series representation of G. Discrete series representation are those representations which are isolated points in the temporal due. Okay, so this is just to give you a different viewpoint of how should we understand the index of Dirac operators on the non-compact symmetric space. Okay, so instead of to attack this temporal due directly, a better way to understand this temporal due is using the reduced group theta algebra. This is how we use the non-commutative geometry tools to understand this problem. So when the temporal due is Hausdorff, for example, if the G is a complex group, for example, if G equal to SL2C or GLNC, then it is the always case. This theta algebra, this reduced theta algebra, is Morita equivalent to the continuous function on temporal due, which equal to vanish at infinity. So that's why. So it suggests that in order to understand this one, we can use this non-commutative object to its a replacement, or it's a better way, provide us a more convenient way to understand the temporal due. Here's a theorem. It says that the spectrum of this reduced C-star algebra is the temporal due of G. So thanks to this, instead of to study the K-theory of this temporal due space, as I said, because the temporal due in general, it may not be a Hausdorff space, so it may not be so nice. So we will consider the K-theory, try to study the K-theory of the reduced C-star algebra of G. Okay. So now it's we can talk about the Kasparov isomorphism. So let's R spin Ks is the Grothendieck group of the spin modules. So it's just difference of the two spin module. And if G mod K is a spin, this group is isomorphic to R of K, or the irreducible representation of K. Because as I said, this if G mod K is a spin, every spin module is in the form of the fancy S. S is the unique irreducible representation for the Khalifa algebra tensor with representation. This is K representation if it is spin. But if G mod K is not a spin, then this group is different from R for K, because you have to go to the representation of the twofold cover K tilde of K. But if it is spin, then this one is just R of K. So Kahn and Kasparov separately, they conjectured that, and this is first proved by Wasserman and Lafogue. They use completely different the method to prove this theorem. Says that if G is any connected linear reductive Lie group, the index map is an isomorphism. Okay. And in 2000, I think it's 2003, Schubert and Echthoff and Nest, they prove the above theorem is true for almost connected Lie group. Almost connected just means that it has a finite many connected component. And our work is we follow Wasserman's approach. The proof outlined by Wasserman, it used a lot of detailed representation theory, so involves many information about its temporal due, and we follow Wasserman's outline and trying to fill some missing informations to make his approach complete to this theorem. This is our goal of this project. Oh, okay. So next. So in order to so Wasserman's approach is to get a more refined structure, or to understand better the structure of the reduced group C-star algebra, and to understand the structure of the group C-star better, we need to understand we need some representation theory information. So the first one we need is a parabolic subgroup. So let's A to be a maximal abelian positive definite subgroup of G. So here you can just consider A, for example, in most cases, you can consider A to be the subgroup of G which are diagonal. So you can consider A0 just as the diagonal matrix. And we can fix an element X in the Lie algebra. Every choice of this X, we can define some subgroups. The first one is N. This is defined as follow. And this one turns out to be a nilpotent subgroup. So maybe, for example, if it is SL2R, we can take this N to be something like this, 1, 1, and star. This is a nilpotent subgroup in the SL2R. Okay. And L is element satisfied. So in this case, L is order diagonal. A 0, 0, 1 over A. Okay, so this is here, A is in R. So L is known as the Levy factor, and the parabolic subgroup is the product of L and N. So the parabolic subgroup P is L times N. And because this L and N, because both L and N determines the P, so for different choice of P, that is equivalent to say different choice of the X and also different determines different N and L. So we will just use this subscription. So LP and NP are the Levy factor and nilpotent subgroup associated to P. Moreover, we have this well-known Iwasawa decomposition. So in the SL2R case, we can decompose this L into this is, so in this case, M is just plus minus 1, 0, 0. For SL2R, M is just the subgroup isomorphic to Z2, and A is this, it's just this group, A 0, 0, 1 over A, with A greater than 0. So this is our decomposition of L. So that's this is the decomposition. This MAN is a decomposition for the parabolic subgroup. And in particular, it is always the case that MP always has discrete series representations, no matter G has discrete series representation or not. M, for any parabolic subgroup, this M always has discrete series representations. Okay, so here's one theorem, and why parabolic subgroup are so important is because theorem by Langlands. So it says that every tempered irreducible representation of G can be embedded into a parabolically induced representation. So here, use this here, sigma is a discrete series representation of M. Okay, and you fix the discrete series representation of MP, and you fix a unitary representation. In this case, AP is always isomorphic to Rn. So it just have the structure of the vector space. So its unitary due is the same, it's simple. So you choose a unitary representation of AP, which is Rn, and you choose a discrete series representation of M, then you do parabolic induction. So you get a G representation. So this one is a G representation. But in general, G representation in this parabolic induced representation may not be, it is always unitary, but it may not be irreducible. So it may decompose into several irreducible representations of G. But the theorem by Langlands just says that every irreducible temporal representation can be embedded into such a parabolic induced representation. Okay. So that's this, with this parabolic subgroup, it helps us to understand this temporal due. So the temporal due is can be, so this is a work of Harshchandra and Langlands. The temporal due is something like this. So it's where this P, so this P and the sigma varies from over, or parabolic subgroup of G and the sigma varies over all the discrete series representation of M, that P is P has P equal to MAN is the Iwasawa decomposition, as I just discussed, and sigma is a discrete series representation of M, and this while group associated to sigma is element such that it fix the Levy factor, fix LP, and also fix this discrete series representation of M and divide by LP. So this is always a finite group. This group acts on AP hat. So that is to say, this temporal due, it is always in a form of a vector space divided by some finite group. So in a simple case, if it is SL2C, so this there's only one P, and the sigma is labeled by natural number N. So this is given by like some lines. So this is N equal to 0, N equal to 1, N equal to -1, N equal to -2, and so on. This is N equal to 2 and N equal to 3. So the while group map this line to this line, and the map to this line to this line. So you can identify 1 and the -1. And for 0, this while group map from the positive part to the negative part. So that is to say, in this case, the temporal due for the SL2C, the temporal due, because the while group action is something like this one, with one half line correspond to n equal to 0, and n equal to 1, n equal to 2, and so on. So this is the structure of the temporal due. Okay, so that with the description of the temporal due of G, we can have with this we can know better the structure of the reduced group system the algebra. So that fix a parabolic subgroup P and a discrete series representation sigma as phi varies, we can get a family of morphism from the group system algebra of G to this one. So this is varies by a hat, and this is the parabolic induced representation. This K means the compact operators on this G representation, and we take the W sigma invariant part. By a work of Claire, Crisp, and Nigel, they showed that the group system algebra is isomorphic. The structure can be described in this way. Use the representation theory if you know the temporal due. So this P sigma varies from over all the parabolic subgroup and the discrete series representation of M, and this one. So this is a structure of the group system algebra. This isomorphism is actually given by Fourier transform. So this is like after you apply the Fourier transform, then what you will get is the same. It tells you some structure of the group system algebra. But it's not. This is not end of. Although we have a nice structure of the group system algebra, but this is not end of the story. The reason is that this sigma, so this fixed point. So the problem is that how the sigma acts on this space is in general it could be difficult to determine. That is the hard part. And to understand this, although sigma is just a finite group and this AP hat is just a Euclidean space, but how the finite group, this wild group, acts on this space, what is the fixed point algebra? It is still difficult to determine. So to determine this one, we really need some representation theory tools. So that the representation theory tools, the first one we need is the Napstein theory. So that for parabolic induced representation, so here sigma is the representation of is a discrete series representation of MP, and phi is in AP hat. So these are parabolic induced representation. So for any W in a wild group which fix sigma, that we can define it induce an intertwining operator. So it maps this parabolic induced representation to this one. So that is intertwining operator. So that in this case, we will view this parabolic induced representation and this one are the same. Are the same. And for this subgroup W sigma, because we wanted to understand how the W sigma acts on this algebra, and we need to define there's a subgroup. So this is a difficult part. That is in this W sigma, it has a normal subgroup such that it induced intertwining operator acts as a scalar on the representation, parabolic induced representation, where there's a phi. We take a phi to be trivial. So that this, if it is a trivial, if a phi is a trivial, then for any W in here, it maps this parabolic induced representation of 1 to itself, because WX1 to 1. So for those elements which acts as a scalar from this 1 to itself, then we define this is to define this subgroup to be W sigma prime. And this is a normal subgroup. And the R group is this sigma. I think Napstein shows that this wild group has a following structure. It is has a R group. So this W sigma can be written as the R sigma cross product with this normal subgroup. And this R group is very important. This R group, on one hand, this R group is very simple because this R group is just a product of Z2. So it is always in the form of Z2 times Z2 times Z2. And this R group are very subtle in the sense that this R group actually measures the reducibility of the parabolic induced representation from trivial phi. So as I said before, this parabolic induced representation in general, it is always unitary, but may be reducible. It may reduce into several irreducible G representations. And this one tells you how many G representations it decomposes into is the same as the size of the R group. And so that is to say, any representation, G representation induced from trivial phi, it can be only decomposed into 2 irreducible components, or 4 or 8. It has to be power of 2. Okay, and this R group turns out to be very important for us to compute the K-series of reduced system algebra in the following sense. Okay, so now if we know the structure of the reduced system algebra, it helps us a lot to compute its K-series, because following Wasserman and by the work of Claire, Chris, and Nigel, up to Morita equivalence, this reduced system algebra is Morita equivalent to the following. So remember now, this on the right-hand side, this algebra is much simpler to understand because this one, a p hat is always Rn. It's just a Euclidean space, and this W sigma prime is always a finite group. And this even better, this R sigma, as I said, is always the case of Z2 product of Z2 of Z2. So now with this, we have a much better description, or we can understand up to Morita equivalence. The system algebra on the right-hand side are simpler than the system algebra on the left-hand side. And by the work of Wasserman, so the K-series of the right-hand side, because they are Morita equivalent, is the same as the K-series of the right-hand side. So because all these elements are much easier to describe, so the K-series of the right-hand side, in principle, should be simpler to compute. In particular, it's not difficult to prove if this sigma is non-trivial, as long as it is non-trivial by some homotopy technique, because this space will be contractible by some trick. You can show its K-series is always trivial. So that is to say, as long as this subgroup is non-trivial, its K-series is always trivial. So which means that if you want to compute the K-series, you only care about those components, those P and sigma, such that W sigma prime are trivial. So that is to say, in order to compute its K-series, we only need to understand when this subgroup will be trivial. And it turns out to understand this subgroup, when this subgroup is trivial, turns out to be quite non-trivial. This is the missing part in Wasserman's outline, that is to analyze, to characterize when W sigma prime is trivial. And turns out we need some representation theory tools. The one we use here is Vaughan's theory of minimum K-type and Napstein theory of intertwining operators. Using these two theories to help us to understand when the W sigma prime is trivial. Okay, now let me introduce the definition. So we call the component of the temporal due associated to P sigma. Every P sigma corresponded to one connected component in the temporal due. We say it is essential if it's associated W sigma prime is trivial. In this case, the essential component will contribute a generator to the K-series. It's because the following theorem. If this one is essential, it means that this W prime is trivial, then there's no W prime. So this component up to Morita equivalence, this system algebra actually is always in this form, because use the intertwining R operator, we can know the R group acts on this R by reflection. So this one is isomorphic to this one. And in this case, its K-series can be computed directly. So the K-series is isomorphic to Z. So that's why for those component, for those essential component where W prime is trivial, it always contributes to one generator in the K-series. Okay. Okay, now we now understand when component in the temporal dual will contribute to the K-series. Now we wanted to relate it to the the other side of the Kasparov theorem. So if let S to be a irreducible spin module, and P sigma is a component in the temporal dual. Okay, so this S is the spin module is the is the module we use to define Dirac operators on the symmetric space, and we say they are matched. The S and this component, they are matched if the following two conditions hold. The first one is that the parabolic induced representation tensor with S take the K invariant part is non-zero. So this space is non-zero. And the second one is that the Dirac operator vanish. So this we can get for any fixed sigma as phi varies in this AP hat, we get a family of representations such that they all have the same K type. When I say K type, means that their restriction to K are all the same. No matter for different so here, one comment is that this is a G space, then it is of course also a K space. Phi 1 restrict to K is the same as P sigma for phi 2 restrict to K. So in this case, we denote them by just we can forget about the parameter phi. So we say they're matched if this one is non-zero and the Dirac operator vanish for some phi. In fact, by some work, you can show if it vanishes for someone, in fact, if it has a kernel, means that it has a kernel. In fact, in this case, it can only when this happens. In fact, it happens, only happen when phi is trivial. So that is to say, in before I talk about a different viewpoint about the index is we view it as a vector bundle on the temporal dual. So this matching theorem just says that on each component, if you have a spin module, they are matched. If this vector space as a space, it is non-trivial, and the operators between these two space has support, and its support is at the 0 point. In this case, the index bundle is non-trivial in the K series. So if you use the viewpoint of the vector bundle on the temporal dual, then the index bundle, what I just said, if they are matched, it has this part is non-zero and this operator vanish at 1 point, then this one it will be non-trivial in the K series of the temporal dual, roughly speaking. So that's now our theorem. This slide is our main theorem. It says that if G is a connected linear real reductive Lie group, then every essential component. So essential component, as I explained before, those will contribute. The essential component will contribute. So is W sigma prime is trivial, and this component will contribute to the K series of group system algebra of G. And for every essential component, there is a unique irreducible spin the module such that they are matched. And every irreducible spin module, there is a unique essential component such that they are matched. On the other hand, as I said, essential component correspond to the generators of the K-series of reduced group system, the algebra of G. So what this matching theorem will show that S of KS spin. So this is the Grothendieck group of spin modules. This will show this one is isomorphic to the K-series of group system algebra of G, because on this side, the generator is given by essential component. So the generator in the K-series side is given by essential P sigma. On this side, it's just all the spin modules. So that this matching theorem is tells you these two groups are the same. Okay, so this is okay. In order to prove I'm not going to tell you the proof of this matching theorem, but the key ingredient of the matching theorem is Vogel's theory of minimum K type. Our main tool is the Vogel's minimum K type. So let me just say a few words. What is minimum K type play a role here? Because for every P sigma, we can associate to parabolic induced representation. And then this is the G representation, and we can talk about. So this is the G representation. It if you restrict to K, it decomposes into infinite many K representations. Then there's a minimum one. Come in the sense of Vogel, we call it a minimum K type. So it's just all the one K representation which appear in the decomposition of this G representation and which are minimum in suitable sense. And this minimum K type somehow tell you some information about this representation. So we relate, what we relate is that, what we do is that we, for this minimum K type, we relate if the minimum K type is regular in some sense, will lead to this group is trivial. This W prime group is trivial if this minimum type is regular in suitable sense. So that's why how we use the minimum K type to relate the essential component and the K types, and this will help us to establish this matching theorem. And this matching theorem will help us to complete the proof of the concave prop theorem in using the strategy of the Wasserman, which is knowing which is analyze the structure of the group system algebra of G. Okay, so my last few slides will just give you one example of the SL2R. Just tells you, explain to you in examples what's going on here. So if G equal to SL2R, the maximal compact subgroup is SL2. This is just a circle, a billion group. It's just isomorphic to a circle. And the temporal view of the SL2R consists of two parts. One is discrete series representation, labeled by all non-zero integers. And in addition to the discrete series representation, there are two continuous series representations. So those are, so these are for the continuous series representation, you have to choose a parabolic subgroup which is not equal to G. So in that case, in this case, M just isomorphic to Z2 and A is isomorphic to R. Okay, so in this case, so Z2 has only two representation, trivial one and non-trivial one, will be denoted by even and odd. So different choice of the representation of M will give you two different family. So, and the wild group in this case is the W sigma. It's always Z2. So this intertwining operator will identify the pi sigma phi and pi sigma minus phi. Here phi is the representation of A hat, which is isomorphic to R. And what is special is that if you take epsilon to be odd and take phi to be trivial, then this representation is no longer irreducible. is decomposed into two representations, which are known as the discrete series representations. So this is the temporal due of the SL2R. Here's one picture of the SL2R. So those parts are discrete. So those are called discrete series representation, the minus part. And these are the two continuous family. So the spherical one is known as the even part, and the non-spherical one is the odd part. And because the reducibility at the endpoint of the odd part, this endpoint decomposed into two points. Those are known as the limit of discrete series representation of G. So this is the picture of the temporal due. And the structure of the reduced C-star algebra of the SL2R is given by this one corresponding to the even continuous part. That's series. And this one is the odd continuous series. And this part are discrete series. And you can see that if you want to come the essential part, because this one won't contribute to the K theory. This is this Z2 is W sigma prime, and this one is the R sigma. So in the odd part, it has no W sigma prime. So this is essential part, which would contribute to the K theory. These are also all discrete series. Of course, there's no wild group. So it's essential part. So the essential part is given by this one and all the discrete series. So this is the essential part. And because for SL2R, G mark K is a spin, so this group, Grothendieck group of the spin module is the same as the representation of K, which is the SL2, which isomorphic to Z. So the Concaspar theorem just says that the K theory of reduced C-star algebra of the SL2R is the same as Z, which is the character ring of the SL2R. So this discrete series will map to all the non-zero n, and this for n equal to 0, the generator is given by the odd principal series. So this is one example of the Concaspar theorem. And thank you. This is all I want to say.
Well, thank you very much. Are there any questions or comments for Yanli?
Yes, I just want to, because I'm not aware of the exact status of things in the p-adic case and in the adelic case. So what is the situation there?
Oh, I think in the p-adic case and adelic case, even the structure of the group C-star algebra, I think there's some progress under some assumption. I think some people have a similar theorem, like the structure theorem for the group C-star algebra. But in general, I think it's more complicated. But that is definitely one direction we wanted to work on in the future.
Especially the adelic case should be, accessible once the p-adic case will be known, and that
yes, yeah, I agree.
I mean, yes.
One thing I know, I think is for SLNPQ and GLNPQ. I think we have a similar result, but for general p-adic group, I don't think there's a complete the answer to this question.
Adelic, then it should be okay, I presume also.
That I guess, but I don't know for sure.
Okay, so any other question for you?
Sorry, just a stupid question. So I was confused about this last example. So the representation ring of SO2 has lots of representations, right? Not just, so why is the representation ring Z? Isn't it like?
Oh, it's because it's just a circle. SO2 is just a circle. So it's just a circle X on C. It's characterized by the weight n, right?
Yeah.
With n is the Z. So for every the integer, it gave you different representation.
Yeah, so shouldn't the maybe I don't understand. So it's the representation ring over the group Z, right? Or
Yes. Yeah.
The left-hand side there should be SO2 hat is Z, but the representation ring is Z square bracket Z,
Oh.
which is a Laurent polynomial ring.
I see.
Yes,
Okay,
yes,
yeah. So
yeah,
that's
yeah,
my
yeah.
question. Okay, thanks. Great.
Okay, so any further question for Yanli? Okay, so if not, yeah, let's thank Yanli for the wonderful talk.